which isn't exactly what I want to do because I've got this all tied to my camera. This is
Oh, okay,
OBS,
gotcha.
yeah.
All right, well then everybody can just pin Steven's screen so that
Yeah.
it's the biggest one.
Sorry about that.
No worries.
Yeah, so to kind of kick things off, I'll give you a quick background on me. So I am a backend engineering team lead at Customer.io. We're a marketing platform based globally. We were remote before it was cool, or before it was mandatory at least. And in my job there, I am both a manager as well as working as a scalability engineer. So I build out massively scaled systems in Go, and have been doing that there for now 7.5 years. And prior to that, I was a freelancer working in a variety of languages. Go is something I picked up at Customer.io, and I definitely would not look back. So that's me. So I wanted to kick off talking about Testify, more so talking a little bit about why tests, because especially coming from my previous background where I did a lot of web crawling, which isn't something you can really do great tests for. So I wasn't actually really the kind of person who wrote a lot of tests. And so that was something that I picked up in the Go world, which is a very nice place to pick it up since they're natively built into the whole Go framework. And so, I mean, this was a question that was on my mind a lot. What's the point in writing tests? They take a long time and they're kind of annoying to write. So what do we get? So there's, your like general thing out of a test. You're verifying your correctness of the code that you're writing, so you can feel confident about shipping stuff to production. That confidence also, I would say, translates over to being able to move more quickly, even though you're writing 2 to 3 times as much code sometimes to write a test. It means that as you're adding more and more functionality to whatever you're writing, you can feel confident that changing one thing isn't going to cascade into breaking everything else. Differently from that, I've found that writing tests actually can really help understand the problem space that you're working in. So what's really kind of an interesting thing about writing a test is that you're writing kind of the opposite of what you're trying to do in the code. So you're writing a test to say, does this code do this thing? And then you're writing the code that does that thing. And so it's kind of like two halves of the same problem, which can be kind of an interesting environment to work in, because if you get stuck on one side or the other, you can go and write some tests to cover stuff that you're trying to understand how you might write the code for. May help give you some ideas as to how to build out the actual functionality you're trying to build. Tests also let you do kind of a sloppier job with your code. If you write good tests, then you can write code that doesn't look great, but gets the job done. So you're like you're covered for the functionalities there, and then you can kind of go back and say, how do I refactor this to make it better? And then finally, the main thing that I would say tests are good for is being like a historical repository of regressions and things that you're trying not to repeat in your code. So the more that you've got tests kicking around, the more that if you fixed a bug a month ago and then you wrote a test to make sure that bug doesn't show up, then nobody else in the organization or on your team is going to be able to make that bug happen without running into your great test. So that's why you should write tests, but might as well take the devil's advocate side as well. Why shouldn't you write tests? And I mentioned this already. Tests take time, and I would say tests take a lot of time. Generally, when I'm writing code, you can write a bunch of code, or a small amount of code that does a very specific thing, and I got tons of examples of that. And then the test is going to take another hour to write. So you might spend 5 minutes writing the actual logic and an hour writing tests. That seems like a kind of asymmetric use of your time. Tests also take maintenance. So it's not just, I talked a little bit about regressions. It's not just I write a test and it's going to sit there and magically solve things for me. If someone goes and refactors a big part of your code base, probably they're going to need to work with your tests as well to make sure that they're fixed, or that if they're failing in the right way, and that they're failing because they're actually representing behavior that has changed in a bad way, but sometimes you actually want that behavior to change. And so tests are a bunch of work. They're likely to, over time, end up being a lot of what big changes look like in your code base. So if you go in and you're writing a new module in your application that touches a bunch of other parts of the existing code, you're likely to go and run into a lot of cases where you may need to go tweak a bunch of tests, or a bunch of tests start failing, and so you spend a lot of time dealing with other people's tests or dealing with tests that you wrote previously, just in order to get this whole brand new thing kind of in place. So what's interesting is you could take the perspective that tests are the best and covering stuff with tests is a great idea. I mean, it sure sounds like a great idea. Making sure that everything that you write is covered with a test means that you kind of have representative behaviors of everything you wanted to do. So you could go to your product person and say, yes, you told me that you want this calculator to do addition and subtraction and multiplication and division, and I have tests that prove it can do all 4 of those things. But sometimes tests might not really be bringing value to what you're trying to do. So again, coming to something as primitive as those, maybe you're working with multiplication, for example, and you have a test that shows that you can multiply small numbers and you can multiply big numbers, and you can multiply small numbers by big numbers and big numbers by big numbers, and the maximum size of an integer can be multiplied by the maximum size of another integer, and it works out properly and comes out as a big integer, and nothing freaks out. Some of those are useful. So things that are testing the very edges of the system, generally very useful, like that maximum integer. If you've looked a lot at things like integer sizes, so if you're working like a 32-bit integer and you multiply that by another 32-bit integer and they're both too big, you get integer overflows, which cause all sorts of beautiful, wonderful bugs when you get into like running stuff in production. But maybe you don't need to have a test for every single one of those cases. So you could test, for example, that so if you have parameter A and parameter B and you multiply A times B, you probably don't need to test that you can have a small integer in A and a big in B, and then a big one in A and a small one in B. Because of the transitive properties of multiplication, you really only need to test one. So I think all that to say, don't write tests that aren't really adding value to the code base. And on another kind of tangent to that, if you're thinking about value adding, some of that is also to your coworkers. So maybe you're writing a bunch of tests that cover every possible case of a system, and you come to a code review and you've committed 10,000 lines of tests for a 10-line change in the code, and it covers every possible thing that could ever happen. Maybe that's useful. Really depends on what you're working with, but you really definitely need to consider someone's going to have to look at this code and reason out what it does. Someone's going to have to deal with maintenance in this code, and someone is probably at some point going to have to evaluate whether these are still of value when they change something. So they decide, oh, actually, we don't care if our thing can multiply anymore, or we don't care that if it can multiply big numbers. We're limiting it to numbers under 100. So maybe that's going to cut out 90% of that work that you just did. And so kind of considering how much value you're adding with a test is very important. And then equally, sometimes test behavior can be very hard to define, especially if there's a lot of moving parts. And this comes into like integration tests. If you're working with something like, a web server, or a lot of what I do, because Customer IO is primarily, or started off as an email platform, is working with SMTP, which is the email protocol. And a lot of things can go wrong because it's a very chatty protocol. So you kind of like say, hey, I want to send an email. It says, cool, you can go ahead and send an email. And you say, hey, I'm going to send it to this person. They say, cool, you can send it to that person. And so there's like a lot of different steps going on. So it can be really tricky behavior to check and define and represent. And so maybe you just want one test that kind of treats that as a black box and says, okay, I'm going to assume that everything else in there kind of works, and then I can move on from there. So I think always considering when you're writing a test, am I testing something that's so small that it's not useful, or so tangential that it's not useful, or am I testing something that is likely to change a lot and maybe behavior that's only temporary as well? So one of the things that I've seen a lot is testing things like if you're changing like a data structure, so you're changing something to adding a new field to a JSON object or something, and you might want to test that everything works with that new field. But eventually, your whole system is going to be built on top of that field, and so that's also an environment where you might write a test temporarily, so you're testing it kind of for yourself, and then taking that test and destroying it afterwards, or maybe just saying this is something that is better handled by a QA team or by myself clicking around in the app. Really kind of depends. All that to say, I think there are a lot of situations where you shouldn't write a test, and I think it's important to call that out, because chasing that 100% code coverage is likely never going to be a great use of your time. Kind of that whole 80-20 rule. You can definitely get a lot of value out of writing tests without covering everything. So moving on then to testing in Go, which is sort of what this is about, except we're going to talk a little bit about the specifics of Testify. So when testing in Go, there's kind of like 3 high-level primitives, maybe 4 if you want to talk about testing.m. Most of the stuff that we're going to be talking about is the testing.t, which is your like standard built-in Go testing thing. When you run Go test, it looks for stuff that takes signatures that look like they accept the testing.t, and it'll run them for you. Some other cool things that are kicking around in the Go tests library, testing.b, which is a benchmarking system, which can be very, very useful if you're looking at performance, and allows you to kind of check whether your code, or maybe if you're refactoring some code, you can quantifiably show that, yes, this refactor was of value because now it's 10 times faster. And we can talk a little bit more about that when I get into hopefully some live coding in a bit. And then coming up in the next version of Go, just as like a plug for some exciting new things in the Go world, is testing.f. You may have heard of fuzz testing before, maybe not. It's a little bit of I think a fringe practice that I would say is generally associated with crypto people, or crypto in the cryptography and not cryptocurrency sense, and operating system type things. So a lot of what you do when you're doing test fuzzing is kind of taking some of that, like figuring out what are the edge conditions of a function or a method, but doing it automatically. And so fuzzing frameworks will kind of, you say this accepts a string, it'll say cool, I got you, and it'll send every possible type of orientation of strings full of weird Unicode characters and strings that are empty and all that kind of stuff. So it's kind of a useful way to really stress test maybe stuff that you're concerned might be really easy to break or kind of dangerous in production. I think people have used fuzzing for things like SQL injection and query injection, and like all sorts of security type situations. Then the fourth thing that's not on this slide is testing.m, which is not used nearly as much that I've seen, although it's kind of depends on the way that you're using tests. But testing.m kind of lets you set up some stuff prior to running a test suite. So in every one of your packages, you can have one test main file that takes the testing.m, and that's what actually ends up calling the like test runner. But if you wanted to do some setup, like starting up your local database or spinning up some external service or just setting up some like local configurations, testing.m would be something that you could do that in. So then what do tests look like? This is one that came out of a premailer library that I was working on. Premailer is a Ruby package that does a bunch of parsing on HTML and makes it ready for sending in emails. So this test is specifically checking that the code that I wrote is able to remove comments from an HTML block. Or actually, I think specifically this one is testing the opposite of that. So it's testing whether if I disable the remove comments functionality, which I think is the default, that it'll still leave in HTML comments. And so this kind of is your standard example of a very verbose setup with very little payoff in a Go test. So you kind of got here at the top, we're setting up an HTML body and then creating a new premailer object and then setting the feature of the premailer object and converting the text that we passed into it into the inline CSS and then parsing it and then pulling out all of the nodes of the HTML. And then finally, we do a t.error if we didn't get a comment. So very verbose for what turns out to be a very small feature. And we can talk a little bit about how frameworks like Testify help out with that. Another thing that you might see a lot of are what are called table-driven tests. So this is where you know what the whole flow is of a test. So in this case, it's a function that takes a camel case string and converts it to a snake case string. And so you kind of know, like, I can intuit or kind of decide on paper, here's what it would look like if this one was changed to a snake case and this one, and then you can write all those out. So you say this is a camel case string, and you know it's gonna, what you want it to look like is that. So you kind of define out all of your test cases, and then you can use this t.run, which is kind of a sub-test runner in Go. So you can like create a second layer of tests inside of a single test. Call the function, call your test logic, and what you end up with is it will run all three of these cases kind of for you within the single test. So it's a great way to encapsulate tests of different things about the same function. So you kind of like a SIMD approach. So a single handler. So we're always calling this camel case thing and checking what we expect, but then you kind of change up what the actual data is that's going into it. So outside of that, so those are kind of like writing tests based on the base Go version, Go stuff. Well, I figured I should also call this out. This comes from the corpus of a really great course called Test with Go by John Calhoun, and highly recommend. It's a great, like 37 hours of videos or something about everything you can imagine about Go testing. And great to check out. And I believe all of the source code for that is available as well on his GitHub. So if you wanted to just look at look through some of his example code, that's there as well. So getting back to other paradigms of testing. So there's kind of like the Go standard, which is, do a bunch of stuff, check it, and then error when something doesn't match what you expect. There's also, if any of you have worked with Ruby or Rails, you've probably seen RSpec. So spec tests, or what's called behavior-driven development often, is where you kind of have a very verbose DSL, which means specific language around testing. So it would be, you can almost read the test like it's kind of like a spec document from like a product person. So it would say, given that I have a calculator and that I've passed in 2 positive integers, the result should also be positive when I'm multiplying, and the results should also be positive when I'm subtracting, or the result might not be positive when I'm subtracting, things like that. So it's a lot of like very well defined and described steps. Usually the actual stuff being tested tends to be fairly short. So you kind of get a bunch of setup built into these like larger test blocks that you can kind of read like almost like a spec document. Another one that we've just recently started working with at Customer IO is called approval testing. This is kind of an interesting new approach that we've seen, where you write kind of like, if you were to look at that premailer thing, you might see all of it except for that last bit where I was actually testing the result. And so what an approval test system will do is you just kind of generate some JSON at the end. So you'd say, here's the result, whether it's just like a JSON value. We use it specifically for API tests. And so you might send a request out to an API and get back the result. And then the first time it's run, it will generate a file that says this was your result. You take a look at it. And then on subsequent runs, instead of having to change up anything, it's just going to change that file. And so nothing changes in the test. You end up having a kind of a file you can compare, and it gives you kind of a direct JSON diff, which is a little bit nice to look at, especially when you're working with API type responses. And then finally, we 20 minutes in, we get to Testify. The Testify, I would kind of classify as being a helper package. So it kind of sits on top of the normal Go testing framework, and gives you a bunch of the things that otherwise end up being kind of verbose, makes them nicer, gives you some fairly useful functionality that that lets you write tests faster and write smaller tests, which is definitely what we want in a lot of scenarios, because the less code there is in a test, the easier it is to understand generally what it's trying to test. And so there are a few like that. We use a library at Customer called GoCheck as well, that provides a lot of the same primitives. It really kind of comes down to a matter of taste. And one of the things that often you'll see internally at companies is they'll maybe maintain a fork of one of these kinds of libraries that has a lot more primitives that are specific to them. So if at somewhere like Coinbase, you're doing a lot of tests related to specifically stuff on the blockchain, you might have stuff that can check blocks in the blockchain or something directly against output from functionality, which gives you kind of like a second layer on top of. So you'd have like the main Testify, and then you'd have whatever the extra stuff is that's being given at the place that you're working. And that can be a really great way to think about these test frameworks as well. I think as an engineer coming in, is often you'll have the fresh eyes where you're looking at, hey, why does this keep getting repeated? We seem to be having to do a bunch of extra work here. And so adding those kinds of things, like if you see that you're having to check some chain of blocks in some certain way every single time, maybe there's a way that you can add in something on top of this test helper that kind of creates that internal improvement to tests for everybody. So getting into Testify, it's got three major packages we'll talk about. So the first one is the Assert package, probably what you use the most. This is where you're kind of doing a lot of those checks. So if you saw at the bottom of both of the tests that we already looked at, there was kind of like an if this is this, then t.error. These kind of abstract out a bunch of that, so that instead of having to write out those different types of things, you can have very obvious, like, I want to know if the length of the camel case one is always less than the length of the snake case one, which it should be because the snake case is adding the extra underscores. Then you have assert.less. Assert.equal is just your kind of standard, did my output match exactly what I wanted to put in? Assert.contains can be a kind of an interesting one. We can get into a better example than this, but basically sometimes, especially when you're doing things like, as I've probably made clear, I do a lot of stuff related to HTML, and writing both the input and the output HTML every time when you're writing tests can be kind of a pain. And so sometimes like there's a specific thing that you're replacing in the HTML and all you care about is that, then you might want to use something like contains, where it's only that. Then contains is interesting as well, because it also, I think, works with both maps and lists too. Not 100% sure on maps, but definitely lists. And so you might have something that's iterating through a shopping list, and you want to check that it contains avocados or something. And so you could do an assert that contains in a situation like that. And assert, which is used kind of across the bounds of programming languages, is usually used to mean that don't continue. unless this passes. And so these are no different. So every single one of these will kind of force exit the test at this point. And there's also a require package in Testify, and that one does all the same things as assert, but my understanding is that the main difference there is that it will actually stop the entire test suite from running. So if there's something that like you don't even want to bother running any other tests, if this one doesn't pass, then that's a fail, and we really need to go think about that. Then you do something like require. And then suite. So I talked a little bit earlier about how when you're working with tests, you may need to do a lot of setup. Test setup can be a real pain, and so using something like suite lets you abstract away a bunch of that setup. Again, kind of the goal being that the actual test here, the test add fresh word, is relatively short and just shows the actual functionality that's being tested. And then all the setup and maybe the tear down, which is cleaning up after yourself, gets abstracted somewhere else. So that's basically what the suite part of Testify works with. And finally, mock. And test mocks can be very useful. A great thing to share within an organization. So you might have a web service or just a really complicated like background service that runs. So in my case, again, talking about SMTP, you might be running an email server within your code that does something very complicated or very interesting. And then you're testing some functionality over top of that doesn't actually care whether the SMTP server works, because that's tested somewhere else. So in that scenario, you might put in a mock instead. And what you get out of that is something that only does what you're telling it to do. So in this case, this is always going to kind of return something predictable. And performs generally a lot better because you're not having to spin up a whole server. Kind of common things you might mock would be a database or a message queue or yeah, like a web server. All the kinds of things that take some time to can set themselves up, configure, be connected to a socket, make sure that the socket is open and things like that. All which adds a lot of time in aggregate. So it might only take half a second to set up everything that you need to set up, but if you have 100 tests, then that's like whatever 50 seconds just spent doing setup to run all those tests. And so instead, if you have a mock that takes a nanosecond, then you're saving yourself an entire minute worth of testing. And in the customer IO world, we kind of ran into a bunch of this fairly recently, where our tests over time started taking upwards of 30-40 minutes to run the entire suite. And by doing some parallelization and mocking out stuff that didn't need to be tested directly, we were able to get that down to like under 10 minutes, which is the difference between being able to kind of actively test using the test suites locally versus kicking something over to a build server and then waiting for an hour, like going for a coffee and hanging out with a friend and coming back and hoping that your tests all passed. So kind of the value in having tests run quickly is definitely tied to overall performance, not only of your application, but also of the individual developers that are trying to make stuff happen in your application. So let's put some of that talk into practice with some code. And I will find VS Code. So we kind of saw this earlier. I think in the slides it was called Camel. I renamed it to Snakeify because that's a little bit better descriptive of what it's actually doing. So this is basically a function that is designed to take something that's in camel case and convert it to something that's in snake case. So you might be doing some fancy stuff that writes Python code based on Go code or something, and so you want to have it in the proper case. So kind of the first thing you might want to do would be to say, okay, well, I need a test for this. And what I want to do is test kind of the base cases of the system. So you want to say, for example, I know that if I have a lower camel case, so like standard camel case string, it should come out as my camel. And hopefully a full camel case string will do the same. So you want full camel case to come out as full underscore camel underscore case, all lowercase. And so with Testify, it's just as easy as that. You're checking the output. And so if you were to go tests, we'll go with the -v flag. That's verbose. And we're going to run just this one, test Snakeify. You can run individual tests or the full suite, but for this, that. And it's very nice about working with Testify compared to working with a standard Go test. So if we compare this to, here's what a regular Go test might look like. So you'd say, results. This if result not equals to my camel, error, add result. Okay. Want camel dot and results. And actually, we're going to do this against the full camel case. That's the actual one that failed. So move those in. And error F, which is a formatted error, so that this interpolated percentage S turns into a formatted error. So here's what error we would get with the Go or the standard Go version. So that kind of gives you this exactly what you write here. So if I hadn't thought to put that information in, it might have just said, oops. And all I would get out would be oops. But instead, if you're working with something like Testify, a lot of that stuff is already built in. So you're working with this, you can get an actual diff from them. So they say, kind of, we were doing this equality check on line 16, which is the full camel case. And then here's what we expected, which was the under. Yeah, I think I did these in the wrong order. Yeah. That test again. So what we expected was full underscore camel case. That's what we wanted to get out of it. We actually got underscore full camel case. What's great about this is we've immediately found an edge case in our function. It looks like if there's a capital letter at the beginning of the string, we're putting underscore before that. So that would be a great reason to go back and look at the code and say, okay, why is it doing that? Well, the way that this code works is it iterates through a string, checks every character, whether it's between capital A and capital Z. If it is, then it writes to this buffer, or this builder rather, an underscore, and then it writes the character. And so every time it finds a capital letter, it's going to write a underscore before it. And at the end, it just treats it as a lowercase string. So if we wanted to, so given that we've now found that first edge case, what we know is we want to correct for the fact that maybe the first character could be a capital and we don't want an underscore at the beginning. So in this case, we might say, well, if edit to this if greater than 0. So we'd say if it's not the first character, so if it's not index 0 as we're iterating through the string, then it's not going to do that. And so now it passes. And that's how we go from red to green on a very basic test. And of course, this would be a great scenario. This is where I kind of had those other things in the sides where you can test all sorts of things now. You could test the lengths of these strings. You could test whether something contains something else. So an interesting one might be when we talked about that we're working with code. So maybe you'd have a code block and you're saying, I want to get rid of all the camel case in my code and replace it with snake case. So you'd have a code block like that. And kind of like I mentioned earlier, instead of also having code block cleaned, should look like something like random number. First of all, it's impossible to type. And second of all, that's going to take a while and also be a little bit more brittle to the things that I actually care about. All I care about is that maybe all I care about at least is that at least one of these is being replaced. So something that I could do instead would be insert.contains, which would be t, say random number generator. Code block. And that's just going to check that somewhere in the result is the random number generator string. Obviously, that's not checking that everything about this thing has been treated properly, which you may or may not care about. Really kind of depends on what you're trying to do with this code, but that would be an example of kind of how you might use one of the more interesting functions of the assert package. And if you are playing around with it in an IDE that lets you, you can see all the various things you can do. So you can check if directories exist. You can check whether things are empty. You can check for equality or errors. A bunch of things that I'm not even sure what they do, checking for false and true, file existence, even stuff related to specifically HTTP. So there's a lot of that stuff has been, someone has gone through and said, hey, what I really need to be able to do is check whether this request redirects when I send an HTTP request. And so you can just use this directly instead of having to come up with what does it actually mean for that to do. And so, or what does it mean that an HTTP request's redirected? I'm not sure. I'm not 100% sure how you would, like off the top of my head, how you would actually go and check that. But I don't need to worry about that because the great and wonderful people over at Testify have already done that work for me. Which, again, kind of coming back to what I'd said about, potentially writing these kinds of methods yourself, is that you kind of can get into the position of being the expert. You answer the question once, what does it mean for an HTTP request to redirect? And suddenly everybody has access to it, which is kind of a really great mindset to get into. Like, how can I make tests easier on everybody else? And that'll really win you a lot of friends. Another thing that's interesting is, obviously, this is one way you could write Snakeify. It's not the only way you could write Snakeify. And what you might want to know is, what's the best way to write Snakeify? And this is where we get into something like benchmarking, and kind of a divergence from Testify, but I think useful to know. So here's what a benchmarking function looks like. I'll put that in the wrong spot. The benchmarks go into the same file as the test file. And what they look like is they take, similar to this whole testing.t on the tests, they take a testing.b. And generally you work somewhere within your benchmark with some sort of iterator taking the b.n value. That's kind of a variable value that Go uses internally to expand or contract the benchmark so that it's not going to take forever to run. So if this function runs really, really quickly, n will be really big and we'll run it a bunch of times and sample that. But if it runs really slowly, it might only run it like 10 or 20 times or something, and just kind of take the average of the speed there. So in this case, what we could do then would be go test bench. I believe it's that. Broke that test, but yeah, for live coding. So one thing you'll note is, oh, sorry, I can. Is that better? Okay. One thing you'll note is that I wasn't actually able to run the benchmarks until all the tests passed. That's kind of a nice little built-in in Go. It can be annoying sometimes if you're like I was doing, just kind of tooling around with the benchmarks, and maybe it doesn't matter to me that code is broken in some way. But but it kind of helps you to stay honest that you're actually benchmarking the right things. Like all the tests that you've already got are already passing. It also helps you because likely what you're going to be doing is going in and refactoring a function. And so if the standard tests that you've got for that function are not working, then probably you don't want to go and benchmark it because it's not even correct. So what you'll see here is it ran a 12 core benchmark in that much time, or possibly that many times, not sure, and took about 243 nanoseconds per run. So that seems pretty good. Honestly, I don't think I'm gonna get a whole lot more performance out of that. But I just heard about regular expressions, and I really want to find a reason to use them. So we'll put in a new one, and we'll call it Snakeify. And instead, what this does is it uses a regular expression, which we don't need to get into what exactly it's doing, except that it's okay, we will get into what it's actually doing. It's taking every instance of a uppercase character preceded by a lowercase character or a number, and replacing it with those two divided by an underscore, and then lowercasing it. And so if we run the benchmark against that one, which it's okay, run that for now. Great reason to double check your code before a presentation. But if you run the benchmark against that one, and assuming that it actually works, we're going to come out with that it takes almost 10 times as long. So this is 30.74 nanoseconds per op. That's almost definitely because, among other things, it's got to compile a regular expression every single time. It's possible that if we move this around maybe and made that a global variable so it gets compiled once, or we used a bunch of the different ways to kind of cache that regular expression, probably going to go faster, but still not fast enough that I would want to replace my string builder version, which only took, I think, 300 nanoseconds or something per operation. So a great way to kind of get familiar with what's going to run fast, what's going to run slow and go. There's a lot of great stuff we could get into with performance testing, but I think this is a kind of useful little trick you can have in your back pocket, especially if you're going and working on a big refactor. So I want to make sure that you all have a chance to ask some questions. So I'm going to go kind of quickly through a couple other things. And so first of all, talking a little bit about how we might work with a suite. And so say we had we wanted to implement a dictionary in the code. So we have something where you can add a word to it, you can get the list of words that's in it, and you can get the definition of a specific word. So I'll kind of gloss over what I've done here, but basically I've made a dictionary that saves itself to the local disk. And so for every word that you add, it creates a new entry in a directory locally. And then it puts the definition into a file called that word. And then when you want to get that out, it'll load it up from disk and print out whatever's in that file. And so if you were going to go in and kind of test that functionality at a very simple level, you might do something like this, where to create your new dictionary. So this is that setup piece. And here we go, checking that when you created it, that it actually created the directory for the dictionary to go in, because obviously, so the directory is not going to be able to create any files. Checking that you can add words and that those create their own files. And then checking that when you go for ask a definition, so for this situation, the definition of the gopher, it comes out with that. And then checking that it comes out with a list of entries that is equal to 2. And I could equally check that the list of entries is exactly the list Gopher and Python. I just chose not to because since I know the way this is being set up, I probably don't need to. So that's kind of an interesting way. Obviously, there's a couple things that we could definitely do here if we wanted to abstract out these checks. So we could do this as a table-driven test. And so if we wanted to instead look at what that might look like, where now, whoa, what's that? That's cool. Where instead of creating and adding these words individually, we're creating a dictionary every time and adding a word to it and checking that the definition is set. We could even take some of this file exist stuff. And so this is kind of taking some of those concepts, but you still have quite a bit of the setup ends up in the individual tests. I don't know how to get my view. That's fine. But what you really kind of want to be able to do is abstract out a bunch of this dictionary bit. And because what I care about is that I can add a word to a dictionary and then check its definition. Maybe I don't really care. Like I could have a function somewhere that checks, that this dictionary exists. But that seems like kind of a lot. And so instead, you might want to make a suite, and that's where you get into something more like this. We'll just replace these. And so a suite would instead let you set up the dictionary in the setup function, tear down the dictionary in the teardown function so that it's not going to stick around in between because it's being stored on disk. And then when we're saying testing adding a word, you can check the word's not there, and then I add the word, and then great, the word's there and the definition is right. And you could also check that the word's not there, or you could check that you can create the word, but then change the definition for the word, because some words have more than one definition. And in our version of the dictionary, words get one definition. It's the most recent one we decided for it. And then we can check that. So that's kind of how a suite would look, and what the nice things that you get out of working with a suite instead of an individual test is that if you do a go test minus v, so you can see when it goes to run this test suite, it kind of breaks them down into the individual tests that it wants to run. So similar to that t.run, which is the built-in in Go. And then kind of gives you a breakdown of those individual tests. So you can say, okay, in this scenario, redefinition of words in my dictionary is not working right now, but adding a fresh word is totally fine. And if we were to look at why redefinition isn't working, it's because I actually explicitly told it not to. I said, if the file already exists, don't add this to the dictionary. So I could say, actually, that's not a requirement anymore. And then go and run my tests again, and they will all pass. And again, it's really nice because all that you're seeing in the actual test body here is the specifics of what the test is actually going to do, and not all of that setup, not all of that teardown. You can kind of assume there's a dictionary, I can work with it, it's empty right now, and every run is going to create a dictionary on the setup, and then remove the dictionary on the cleanup. And so what if instead, this is where I wish I knew how to get back to it. There we go. Let's see, is that well positioned? Yeah. So what if instead you wanted to be able to use this, but you're not using the dictionary directly? What if instead you had, for example, a method like this that's checking the length of like how long the dictionary is going to be. So I have to give this to my publisher and say, hey, my dictionary has this many words in it, which means it's going to take this many pages or something. And so if we were to look at what that function might look like, well, you know that for every entry in the dictionary, if a word is one word plus the length of the definition of the word. So that's kind of how you would do that count. And then when you're going to go in to test that, really what you don't care about is the specifics of the dictionary, and what you do care about is the specifics of the method that you're using to the method that you're using to count that book length. I want to make sure that that's right. And this is where it'd be really great to have a mock, because I don't care that the dictionary is, writing the stuff up to disk and able to read stuff off of disk. Maybe for whatever reason I'm running on a computer that doesn't actually even have a disk. Seems like a pretty wild environment to work in, or maybe the disk is just really slow, or yeah, maybe it's like a network disk or something. So instead, you might make a mock, and a mock is something that would be shared. That's kind of a quick aside. I don't know if you can see this. I don't actually think so. I don't know why I would. Okay. Oh, I'm on the wrong OBS thing. So we look at this. This is some code directly from the Rosetta Bitcoin library, which is one of the Coinbase Bitcoin libraries. And it makes use of a couple of the built-in mocks that they've made specifically for the Rosetta Bitcoin. And these are mocking out something called a mempool service, which is some sort of API. And so it kind of like takes up that space for you, instead of having a directly built-in an object. So you don't have to like set up whatever that service is, because you can just have it as a mock. So then back to code. Go to here. So what a mock might look like then is you kind of define. So we know we're going to like get the list of entries and get the list and get the definitions for each of those in order to count. So we might mock out this define function, which doesn't actually do the grabbing of anything. It uses this syntax, which you can pull out of the Testify stuff. Basically just says, when this gets called with this method, then I'm going to return the arguments that I defined for that. And we can get down to that in a sec. And then for entries, I'm just hard coding in. The only two I'm going to have in there is a Gopher and a Python. And then if we take a look at the method, so this is where those definitions kind of came into place, this m.called. We say, when you call define with the parameter Gopher, here's what I want you to return. And with Python, here's what I want you to return. And then out of interest, I also added Java just to see what would happen if you were to add something that's not defined in the list of entries and isn't going to get called when you call entries. And then I can manually count these 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. So it should come out with 10 because if I drop the Java for starters, should come out with 10 because there's 2 words in the dictionary and a total of 10 words. And so if I test that, see that when it runs against this, it's actually checking these individual calls to define. And this is this m.called that's generating these. So it's saying, I got called these 2 times. You said I should have been called these 2 times. And I should have been called with Gopher, and I should have been called with Python once each and gotten these values. So it kind of like lets you double check that your mock is doing the right thing. And so, but then it's abstracting away the whole actual built-in dictionary, so that you can just test in this book length exactly this. And then if you were to add something that isn't defined, or isn't going to be called because it's not in these entries, it's not officially in the dictionary according to the logic of the dictionary, then you'll get a failure because it was expecting there to be a third call to this defined Java, and that didn't work. So that's the overall rundown of what you get out of Testify. Sorry, it ran a little bit longer than I'd hoped, and I'm happy to stick around a little longer if people have questions or would like to talk about any specifics. I know I kind of breezed through these last couple bits. Hopefully, it was kind of a good intro to what you're about to be up against in the world of testing. And yeah, if anyone has any questions, happy to chat about this. Wonderful. Well, I guess in that case, we can call it here. Thanks so much for spending this hour with me. Hopefully you got something out of it. If you do come up with any questions, feel free to reach out to me. I'm happy to follow up with any of you, and also definitely would like to say best of luck to you as you prepare for your cohort time over at Coinbase. I'm sure it will be a very exciting time, and hopefully that this can help you to come in with a little bit of preparation for at least the testing side of things.
Thank you.
Thank you.
Great. Thank you.
Thank you.
Cheers.
Thanks.
Thanks so much, Dana.